The title of the module, Eulerian Graphs. Today we are going to learn about Eulerian circuits. The origin of graph theory started with the famous unsolved problem called the Königsberg Bridge problem. The Prigel River in Königsberg had two islands linked to each other and to the banks of the river by 7 bridges as shown in the screen. The problem was to start from any one of the land areas and walk across the bridge exactly once and return to the starting point. Euler proved that such a route over the bridges of Königsberg is impossible. Euler created a graph by replacing each land area by a point and each bridge by a line joining the corresponding points. The graph is shown on the screen as you can see. The problem is equivalent to drawing the shown figure without lifting the pen from the paper and without retracing the line and to return to the starting point. This can be interpreted as whether a certain graph has an Eulerian circuit. Let us now see the definition of an Eulerian trail. An Eulerian trail of a graph is an open trail containing all the edges and vertices of a graph. Now let us see the definition of an Eulerian circuit. An Eulerian circuit is a circuit containing all the edges and vertices of the graph. Let us now check whether a certain graph is Eulerian. The definition of an Eulerian graph is a graph that admits an Eulerian circuit is called an Eulerian graph. The definition of a Hamiltonian path. A path which contains every vertex of a graph is called a Hamiltonian path. Now let us see the definition of a Hamiltonian cycle. A cycle which contains every vertex of a graph is called a spanning cycle or a Hamiltonian cycle. Now let us check when a graph is Hamiltonian. A Hamiltonian graph is a graph having a Hamiltonian cycle. This concept is best understood by examples. Now let us see some examples. The 7 bridges of Königsberg is a historically notable problem that was given a negative resolution in the year 1736. This resolution of the problem was given by the famous mathematician Leonhard Euler. Now let us see this problem in detail. The 7 bridges of Königsberg. The city of Königsberg was situated on both sides of the river Prigel and with 2 islands lying on the river Prigel. There were 2 islands, namely Neiphof and Lomis. The city of Königsberg was in Prussia, which is in Kaliningrad in modern day Russia. And the problem was this: what if one could create a walk where one can start at any landmass and travel across all the bridges exactly once and reach one starting point? That was the problem. And this created a lot of interest in the city of Königsberg, and this was not resolved for quite a long time until Leonhard Euler was able to give a very innovative solution to the problem. So he was able to create a kind of graph. This is the graph, and he created a graph in such a way that he created all the land masses as vertices and all the bridges, all the 7 bridges were represented as edges of the graph. So Euler was able to come up with this unique solution by thinking of every landmass as vertices and all the edges as the bridges themselves. So the bridges were represented as edges here, and he gave a negative resolution, which means that he was able to say that such a walk is not possible, because you can see that for this graph the Eulerian circuit does not exist. So the word Eulerian circuit is in memory or it is in honor of Leonhard Euler, who was able to give a solution to this problem. So we already recall that the Eulerian circuit is where you are able to travel through all the edges of the graph exactly once without repeating the edges. Or you can even picturize this in a different manner, that is, you can draw the graph without lifting your finger. So you can see in this graph, you cannot do that. You can start here, you can go all the way to D, you can come to B, but you have to somehow repeat some of the edges in order to travel through all the edges of the graph. So, that is why this graph was the solution to this Königsberg bridge problem was in the negative. So, there is no walk that can travel through all the bridges exactly once. And some would say that the solution to Königsberg bridge problem created and laid the foundation for the subject called graph theory. So, we can thank Leonhard Euler for the subject of graph theory. Let us now see some examples where we will be seeing Eulerian and Hamiltonian graphs simultaneously. Let us look at this example. You can easily see that if I start at V1, the vertex V1, I am travelling all the way to V2, then to V3, V4, then V5, V6, V7, and then back to V5, and then V8, and then V2, and then V9, and then I come back to V1. You can see that the vertices are repeated, but none of the edges have been repeated. That is why this is called an Eulerian circuit. But does this graph allow for the Hamiltonian cycle? Let us check that, and you can see that I do not think that we can do a Hamiltonian cycle, because anyway you will be repeating the vertices, but in a Hamiltonian cycle you are not supposed to repeat the vertices, and therefore this graph is an example of an Eulerian graph, but it is not an example of a Hamiltonian graph. So, this is Eulerian but not Hamiltonian. Let us see one more example where it is neither Eulerian nor Hamiltonian. You can see this example, no matter how you start V1, V4, V5, so E1, E4, E5, E6, E7, E8, E3, but then you will be leaving out the edge E2. Therefore, you start from another position, maybe you can start from here, let us say you are starting at the vertex V4, in that case E4, E5, E6, E7, E8, again you can either go to E1 or E2 or E3, but not all the 3 edges. So, some of the edges are left behind, which means that this graph is not Eulerian. You are supposed to travel through all the edges exactly once. So, this is not possible in this graph. Let us check whether it is Hamiltonian. Again, let me see V1, V4, V5, V6, V7, V8, V4, again we have repeated the vertex V4. So, which means that this graph cannot be Hamiltonian, because you are not supposed to repeat the vertices. So, this is an example of a graph which is neither Eulerian nor Hamiltonian. Now, let us see some more examples. Now, this is a lovely example of a graph that is both Eulerian and Hamiltonian. Let us check for the Eulerian circuit first. Okay? And so, we start from V1, V2, V3, V4, V5, V6, V2 maybe, and then you can go to V4 and then V6. You can see that I have, although I might be repeating vertices, that is allowed in an Eulerian circuit, you are not allowed to repeat the edges. Therefore, I have covered all the edges E1, E2, E3, E4, E5, E6, and I have also covered E8 and E7. So, all the edges have been covered, and therefore, this is a perfect example of a Eulerian graph. Now, let us check for Hamiltonian. You can start here V1, V2, V3, V4, V5, V6, and you can even go back to V2 if you want, but you have already completed the cycle. So, therefore, this is an example of a Hamiltonian cycle. So, you have a Hamiltonian cycle which is able to cover all the vertices of the graph, and you are also having an Eulerian circuit which is covering all the edges of the graph. Therefore, this is a prime example of a graph that is both Eulerian and Hamiltonian. Let us now see an example of a graph which is only Hamiltonian but not Eulerian. You can see that this graph V1, V2, V3, V4, you can easily create a Hamiltonian cycle. So, V1, V2, V3, V4, it creates a Hamiltonian cycle that is touching all the vertices of the graph with none of the vertices repeating themselves. Therefore, you have a Hamiltonian cycle here. But let us check for the Eulerian circuit. You have E1, E2, E3, E4, so far good. Then I go to E5, but then if I have to cover E6, I will have to repeat the edge E3 again. So, I will have to go like this E1, E2, E3, E4, E5, you have to repeat E3 again, and then only you can cover E6. Therefore, the Hamiltonian circuit property is violated here, and therefore, this graph is an example of something that is having a Hamiltonian cycle, but not the Eulerian circuit. It is Hamiltonian but not Eulerian. Now, you can check by yourself whether the standard graphs you have learnt already have Eulerian trail or an Eulerian circuit. Now, as a prelude, we shall prove a simple lemma. Lemma 1. If G is a graph in which the degree of every vertex is at least 2, then G contains a cycle. The proof: let us construct a sequence of vertices V1, V2 and so on as follows. Choose an arbitrary vertex, say V1. Let V2 be any vertex adjacent to V1. Let V3 be any vertex adjacent to V2 other than V1. For any chosen vertex, say Vi, where I is greater than or equal to 3, choose Vi plus 1 to be the vertex adjacent to Vi other than Vi minus 1. Since the degree of Vi is greater than or equal to 2, such a vertex Vi plus 1 always exists. Since G has only a finite number of vertices, at some stage we must choose a vertex which was chosen before. Let Vk be the first such vertex and Vk be equal to Vi where I is less than k. Then Vi, Vi plus 1 and so on up to Vk will be a cycle. Thus, G contains a cycle. Now, let us prove the main theorem which gives the answer for the question in what graph an Eulerian circuit exists. The theorem is: the following statements are equivalent for a connected graph G. Number 1, G is Eulerian. Number 2, every vertex of G has an even degree. And number 3, the set of edges of G can be partitioned into cycles. We shall see the proof. We will be proving the equivalency in steps. So, the first step will be we will be proving the equivalency of 1 implies 2. Now, let us assume that G is Eulerian. Let T be an Eulerian circuit in G. Let V be an arbitrary vertex in G. Each occurrence of V in T as an internal vertex contributes 2 to the degree of V, so that the degree of V is equal to twice the number of occurrences of V in T if V is not equal to V1, and the degree of V is equal to twice the number of occurrences of V in T as an internal vertex plus 2 if V is equal to V1. Thus, the degree of V is obviously it is even, hence every vertex of T has an even degree in G. Now, we shall prove point number 2 implies point number 3. Assume that every vertex of G is of even degree. Since G is connected, every vertex in G has degree at least 2. Thus, by lemma 1, G contains a cycle, say C1. Now, G1, which is G minus edge set of C1, is a spanning subgraph of G in which every vertex has even degree. If G1 has no edges, then G itself is a cycle, and hence point number 3 holds. Otherwise, consider the connected subgraph G1 dash obtained from G1 after the removal of isolated vertices, if it exists. Clearly, every vertex in G1 dash has an even degree. Now, by lemma 1, G1 dash contains a cycle, say C2. Proceed as above until we get a totally disconnected graph, namely Gk. Thus, G is partitioned into cycles C1, C2 and so on up to Ck. Next, we shall prove that 3 implies 1. Assume that G is partitioned into cycles, say C1, C2, so on up to Cn. Consider C1. Since G is connected, there is a vertex in common with C1 and one of the remaining cycles, say C2. Let the common vertex be V. The walk starting at V and containing the cycles C1 and C2 in succession forms a closed Eulerian trail having the edges of these two cycles. Proceeding as above, we get an Eulerian circuit containing all the edges of G. Therefore, G is Eulerian. We have now proved the equivalency of all the statement, and hence the theorem is proved. Now, the above theorem leads to the following corollary. Corollary: let G be a connected graph with exactly 2 n odd points where n is greater than or equal to 1. Then the set of edges of G can be partitioned into n open trails. One more corollary: a connected graph G is an Euler graph if and only if all the vertices of G are of even degree. Next, let us see the definition of the even graph and an odd graph. Definition: a graph is said to be an even graph if all its vertices are of even degree. Similarly, it is said to be an odd graph if all its vertices are of odd degree. Now, the question arises, what graph contains an open Eulerian trail? The following theorem answers your question. Theorem: let G be a non-trivial connected graph. Then G contains an open Eulerian trail if and only if G has exactly 2 odd degree vertices. Furthermore, the trail starts at one of the odd vertices and ends at the other. Proof: let G be a non-trivial connected graph. Assume that G contains an open Eulerian UV trail, say T. Construct a new graph G dash by adding a new vertex x to G, and let us join both u and v to x in G. Now, T union ux, xv is an Eulerian circuit in G dash. Thus, by the above theorem, every vertex is of even degree in G union x. Then in G, every internal vertex of the open Eulerian trail T has even degree except u and v. Conversely, let us assume that G has exactly 2 odd degree vertices, say u and v. Now, let us construct G dash as above. Then every vertex of G dash is even. Hence, G dash contains an Eulerian circuit, say T, with ux and xv as consecutive edges. Now, T minus ux, xv is an open Eulerian trail in G which starts at u and ends at v. There is a simple algorithm due to Fleury in the year 1883 which finds an Eulerian circuit in an Eulerian graph. Now, let us see Fleury's algorithm to construct an Eulerian circuit in an Eulerian graph. The first step is you need to choose a vertex w naught equal to v naught, and step 2 is suppose wi is equal to v naught, e1, v1 so on up to ei, vi. You are supposed to choose ei plus 1 from the edge set of G, subtracting the previous edges. So, e1, e2 so on up to ei, the ith edge up to the ith edge should be taken away from the edge set of G, and you have to choose the I plus 1th edge, ei plus 1. And this ei plus 1 should satisfy certain properties, namely ei plus 1 should be incident with vi, and unless there is no alternative, ei plus 1 is not a bridge of G minus e1, e2 so on up to ei. Therefore, if ei plus 1 happens to be a bridge, you cannot choose ei plus 1. So, that is the condition here. It should be incident with the vertex vi and it should not be a bridge. And step 3 is you need to stop when steps 2 cannot be continued or when it cannot be implemented. So, we will be repeating step 2 on a loop until we arrive at an end vertex. So, this is Fleury's algorithm to construct an Eulerian circuit in an Eulerian graph. Now, let us see the demonstration of this Fleury's algorithm using a graph. You can see that this graph here has got several edges, and we will be starting with a random vertex, namely v3. So, my w can be first my v naught actually here happens to be V3 here. I am choosing the vertex V3, and you can see that there are several edges incident upon here. There are 2 edges here. So, V2 and then V4, 2 vertices have edges with V3. Let me choose the edge E2 here for my convenience, and you can see that it is incident upon the vertex V3, and is it a cut vertex? So, the cut edge, it is not a cut edge, and therefore, there is no harm in choosing the edge E2. So, I am choosing the edge E2. Let me draw this here. So, V3, V2, and then this is the edge E2. Once I have chosen this vertex, let me remove it from the original graph. So, I am going to use this symbol to show that this edge no longer exists. And now coming to the vertex V2, now we are here at V2, this is my V0 actually, so V3 here. Now next step is E2, V2, this is the edge. So, I am simultaneously writing the Eulerian path here. And once I come to V2, I can see that the vertex V1 is adjacent to V2, V9 is adjacent to V2, and finally V8 is also adjacent to V2. Among these 3, I need to choose an edge which is not a cut vertex. So, you can see that E9, if I choose so, once I remove E9, this graph disconnects from the remaining part of the graph, and therefore, E9 is a cut edge, and therefore, it should not be chosen, and you are left with only 2 more choices, namely E10 and E1. Arbitrarily, I am going to choose E1. Therefore, once I have chosen E1, it goes like this. So, I am drawing this here V1, E1. Let me add it to this cycle. So, E1, V1. So, this is the Eulerian circuit I am constructing, and I have added it there, and once I have constructed this, I am removing this here. Okay. So, you should remember that these edges are removed from the original graph. Now, once I come to V1, there is E11 here, and there is only one edge, and is it a cut edge? Let me check. No, it is not a cut edge, and therefore, I can safely choose E11, and I am drawing this here. So, E11 can be added, and this vertex V9 is added. So, put it here. So, E11, V9. Then finally, you can remove this edge now. Now, I come from, I am here at V9. There is only one edge here, E10, and therefore, no harm, it is not a cut edge. Therefore, I can choose it, and therefore, I am choosing it. So, now we are back at V2 here, and this edge has already been done, and therefore, you are left with only the edge E9 and this vertex V8. So, I am going to choose this edge, and I am going to take it here. So, this is E9 and V8. Let me add it to here this sequence in the next line. So, E9 and V8, and this is the, so far this is the Eulerian circuit that we have constructed. Now, we are now at V8, and here the only choice is E8. Can you see it is not a cut edge, therefore, I can add it to the sequence. So, E8 and V5. Now, at V5 you can see that there are several choices for the edges. There is E4, E5 and E7. So, E4, if you take E4, you can see that it becomes a cut edge. Let me first mark this off. If you remove E4, the moment you remove E4 from this graph, this line disconnects from this graph. Therefore, E4 will become E4 is a cut edge, and therefore, you cannot choose E4, but instead you are left with 2 more choices, namely E5 and E7. And among E5 and E7, let me choose arbitrarily E5. Therefore, I am choosing E5. So, from here to V6, E5. So, this is the graph you have constructed, and then at V6 you have only one possibility, namely E6, and therefore, I add it to that therefore, E6, V7. So, E6 and V7, and at V7 there is only one possibility, E7. So, that can be chosen. So, this edge is also removed from the graph, and you are back at V5. V5 you have already chosen E5, and the other edges are also selected. You are left with only E4 here. Now, it is no longer dangerous to choose E4 because now E4 is not a cut edge. Therefore, let me choose E4. And let me add it to the cycle. So, V7 you are left with E7, V5, E4, V4. So, I had missed it in the previous iteration. So, I am adding it to the list now. So, you are now stopping at V4, and now you are left with only one more edge, namely E3. So, you can add that also. So, E3, V4. Therefore, now you have now constructed a Eulerian circuit. We started from V3, we started and we went all along all the edges of the graph, and we have created an Eulerian circuit, as is evident from the original graph and the new construction. So, we have made a faithful reproduction of the original graph by traversing across all the edges exactly once, and we have finished the cycle. So, we finish it here. So, E3 and V3. So, we started at V3, we ended at V3. This is a perfectly constructed Eulerian circuit. Therefore, this Fleury's algorithm is a wonderful method to create an Eulerian circuit in any graph. Next, we shall see an example for a graph in which you cannot construct an Eulerian circuit. So, we have this graph here, and we will be using Fleury's algorithm once again, and I will show you why we cannot get an Eulerian circuit for this graph. So, let me start with the vertex V1. So, vertex V1, there are three choices for edges here. So, there is E1, E5, E4, and let me choose at random. I am choosing E1 for my own sake. So, E1, V2, and I am removing this edge from the original graph G, and now I am here at V2. V2 there is only one choice, namely E2 and the vertex V3. So, I am removing this edge here, and I write E2, V3. So, let me construct this here. So, V1, V2, V3. So, this is E1 and E2. Now, at V3 there are two choices, namely E5 and the edge E3. I can choose at random any edge. I am going to go with E3, and I am choosing E3 here. So, let me add it here. It is E3 V4. So, I am E3 and V4. So, I am done here, and here there is only one choice, namely E4. So, I am going to go here. So, E4. I have chosen this edge. Alright. So, I have come back to V1, that is allowed, but I have to choose only one more edge left here. So, E5 I am choosing that here. So, E5 I am removing this edge also. Therefore, I have constructed a Eulerian, so from V4, E4, V1 and finally E5 and V3. So, I have completed the circuit, the trail here. So, V1, E1, V2, E2, V3, E3, V4, E4, V1 back once again, and then finally E5 and V3. You can very clearly see that you might think that although we have completed the trail, we have completed we have covered all the edges here, all the edges have been covered using this algorithm, but there is one small catch here. You have not ended at the point where you started. So, here there is V1, but you have ended at V3, which means that this is not an Eulerian circuit. It might look like it is an Eulerian circuit because you have covered all the edges. The condition for Eulerian circuit is that you should cover all the edges, but also you should end at the point where you started. So, the second condition is lost here, and therefore, this can be a trail, but not an Eulerian circuit. So, this is an example of where you cannot construct an Eulerian circuit. In this module, we have studied about Eulerian circuits, Hamiltonian cycles. We studied some theorems about Eulerian circuits, and we also learnt how to construct an Eulerian circuit using the Fleury's algorithm. I hope that this module was useful for you to understand Eulerian circuits and Hamiltonian cycles. Please do the assignments and the quiz for this module, because the more we do, the more we learn.